Right, let's do some physics. It's Edexcel, Combined Science, Paper 5, which means it's Physics Paper 1, higher tier, May 2018, 1 hour 10 minutes. It's worth 60 marks. I'll put in the description what's covered in this paper because it's slightly different to what's covered in an AQA Paper 1. But as long as you watch both Paper 1 and Paper 2 content, all exam boards cover very similar content. Now, I had a bit of a nightmare when I recorded this. It didn't screen record. So I've already put the answers onto this PDF. So I'll just be able to blast through it quicker. It might work out better that way. Question 1 here. A student investigates what happens when light travels from air to glass. Figure 1 shows some of the apparatus used in the investigation. It's just standard kit there. In figure 1, angle Y is the angle of, well, it's refraction because that light's been bent. So the answer is D. X is the angle of incidence, just in case you wanted to know. Part 2. Figure 2 is a graph of the student's results. Use the graph to calculate a value for angle Y divided by angle X. So you can take any value of Y and its corresponding angle of X. So what I did here was I took an angle Y of 10 degrees and its corresponding value of X was 16 degrees. So I did 10 divided by 16 and that pops out as 0.625. Part 3. The student concludes that angle Y is directly proportional to angle X. Explain what the student must do to test this conclusion in more detail. Well, it's always best to repeat the test. Now we need to use more angles of X and Y, use some larger values of X to see what Y comes out as. And if it is directly proportional, when X is doubled, Y should double. So for example, when Y is 5, X is 8. So that means if we double Y from 5 to 10, we should double X from 8 to 16, and we do. That's what it means if something's directly proportional, plus it'll go through 0, 0. If we were to triple Y with triple X as well, again, that means it's directly proportional. The line is going up straight. He just needs more angles. Okay, needs to gather more data. Part B. The speed of light is 3 times 10 to the 8 meters a second. The wavelength of yellow light is 5.8 times 10 to the minus 7 meters. Calculate the frequency of yellow light. State the unit. Use this equation. Frequency equals speed divided by wavelength. So pop the speed in, pop the wavelength in. Out comes the answer. It is frequency, so it's in hertz. Question 2. Figure 3 shows a Geiger-Müller tube used for measuring radioactivity. Describe how a teacher should use a Geiger-Müller tube to compare the count rates from 2 different radioactive rocks. Right, well the first thing we need to do is find out the size of the background radiation. Keep the rocks out the way as you do that. Right, now take one of the rocks and place it a certain distance away from the Geiger-Müller tube. Record the count rate for that rock. Make sure that you leave the rock in front of the Geiger-Müller tube for a certain amount of time, because we'll need to do the same for the second rock. So move the first rock out the way, repeat the above steps for the second rock, leave it there for the same length of time, make sure it's the same distance away from the Geiger-Müller tube. Now, in order to get just the count of the rock, remember to subtract the background radiation away from the count rate of each rock. And it's always good to say to repeat the readings for each rock and take the averages. Question B. A hospital uses a radioactive isotope with a half-life of 6 hours. A technician measures a count rate of 80 counts per minute from this isotope. Complete the graph of figure 4 as accurately as possible to show how the count rate from this isotope will change from the time of the first measurement. The first point is already drawn in figure 4. So there was a count rate of 80 at a time of 0. Now, a half-life means it's the time taken for the count rate to half. So in this case, it takes 6 hours for the count rate to half. So in 6 hours' time, the count rate is going to have dropped from 80 down to 40. And then 6 hours later, so at 12 hours, it's going to have halved again down to 20. And then 6 hours later, so at 18 hours, it's going to have halved from 20 down to 10. So that's how you draw your half-life graph. Part C. One radioactive source used in hospitals is technetium. Technetium is produced from the radioactive decay of molybdenum. Complete the following nuclear equation. Now, what you've got to remember is whatever this top number is here, when we get to the right-hand side of the arrow, this number here on the top added to this number here on the top has to equal that number you started with. So this number had to be 99 because 99 plus 0 equals 99. And it's the same for the bottom number. Whatever this number is here on the left-hand side of this arrow, when you add this number to this number, it has to equal that number. So 43 plus minus 1 gives us 42. Question 3a. Figure 5 shows a tuning fork. When the prongs of the fork are struck, the prongs vibrate in the directions shown by the arrows in figure 5. Backwards and forwards like that. Describe how the tuning fork causes a sound wave to travel through the air. You may add to the diagram if it helps your answers. Now the thing is with sound wave, really you just say sound waves are longitudinal waves, and with a longitudinal wave the vibrations are in the same direction to the direction of the wave. Right, so whatever direction the wave is travelling, that is the way that the vibrations are going to be. And I've drew longitudinal waves. You'll end up with compressions, okay, which is a posh word for squashed, and you'll end up with areas where they've spread out, and that's what we call rarefactions, okay. So the air will be vibrating left and right, and as the waves also travelling in the same direction. Part B. The following descriptions describe waves from different parts of the electromagnetic spectrum. Complete each description by adding the name of the wave. Use the name of each wave only once. Each description refers to a different part of the electromagnetic spectrum. I've started by drawing the electromagnetic spectrum. Okay, visible light in the middle, all the other waves. Now, I've also wrote down the rough wavelengths of each of the waves. 1 nm means 1 nanometer. So everywhere you see an nm, that's nanometers. Right, what wave is used in cooking? Right, well cooking, it's either microwaves or infrared straight away. What is used in short-range communication? Well, do you know that all of these waves here are all used for communication? But if it's shortwave communication, the chances are it's going to be infrared. The typical wavelength is 900 nanometers. Right, well it is infrared. Red has got a wavelength of 700 nanometers, and infrared is slightly longer than that, so that's 900 nanometers. So the answer is infrared. Wave 2 is used for cooking. Okay, so again, microwaves are infrared. We've already used infrared, so the chances are it's going to be microwaves. It's used in communication, Yep. And the typical wavelength is 150 millimeters, which is 15 centimeters. So that's microwaves. Microwaves are, the range round about a centimeter long. Wave 3, this is the description, used in communication. Again, it's got to be one of these 4 waves, the longest 4 waves. It's produced by oscillations in electrical circuits. Right, as soon as you see that statement, you know it's radio. And the typical wavelength is 150 meters. Well, radio has got a very long wavelengths. So that's definitely radio. And the final wave is used in medical scanning, right? It's just going to be X-rays or gamma. It's emitted by the nucleus of an atom, right? Well, you know it's gamma. As soon as you see that statement. And the typical wavelength is 2 × 10 to the minus 3 nanometers. Yeah, that's about right. Gamma rays and X-rays do overlap. So that's fine, that's gamma. X-rays are produced by very high voltages. Question C. When white light crosses the boundary between air and glass, it can split up into the colours of the spectrum. Explain in terms of speed why the light behaves like this. So we're talking about shining light through perhaps a glass prism or through a raindrop, and we're producing this spectrum. We're getting an angle of dispersion. Okay, they all refract by different amounts, which makes the white light that comes in split up into the colours of the spectrum. Now, I'm giving you a little bit of background information here. Richard of York gave battle in vain. Red, orange, yellow, green, blue, indigo and violet. Do you know that they've all got different wavelengths? Now, in a vacuum, all of these colours travel the same speed. But as soon as they are in a material, okay, then their speeds will differ. And if you didn't know, so the colours have all got different wavelengths. You can see I've done the wavelengths here. Red's got the longest wavelength. And as we go down the colours, we get to violet, which has got the shortest wavelength. So the longer the wavelength, the faster the speed when it's travelling through a material or medium. So they will refract by different amounts. Different speeds of the different wavelengths cause different amounts of refraction. So you can see that I've underlined those 3 key words. Now you can either talk about this answer in terms of wavelength, or you can talk about it in terms of frequency. So I drew a little picture here to give you a little bit more knowledge. We can see red light has got a long wavelength. As it's travelling through, let's say this is glass, it bumps into 5 different atoms. However, the violet light, because it's got a much shorter wavelength and a much higher frequency, it's vibrating more, and therefore it hits more atoms, okay? Now, if the violet bumps into more atoms, it's going to slow down more. And if it's coming into a material at an angle, it's going to refract more as it slows down. And once again, I'm saying that all waves have got different frequencies. So you can talk about frequencies, the speed changing, and how that causes the direction to change so it refracts. So I hope that gave you a little bit of a background information. Question 4, Part A. The symbol G can be used to refer to the acceleration due to gravity. The acceleration due to gravity G has the unit of meters per second squared. G can also have another unit. Which of these is also a unit for G, for gravity? Now, the way that you should start off with these questions is rack your brains and come up with an equation that's got gravity in. So, weight equals mass times by gravity. Rearrange that to find your target, in this case gravity. So gravity equals weight divided by mass. Get the units of weight, that's newtons. Get the units of mass, that's kilograms. So a unit for gravity can be newtons per kilogram, as well as meters per second. So newtons per kilogram was a choice to choose from, so that's why the answer is C. And that's how you do those kind of questions. Part B. Two students try to determine a value for g, the acceleration due to gravity. They measure the time t for a small steel ball to fall through a height h from rest. They measure t to be 0.74 seconds using a stopwatch. They measure h to be 2.5 metres using a metre rule. Calculate a value for g from the student's measurements. Use the equation. G equals 2h over t squared. Now, you're not supposed to memorise that. What the examiners do is they just make up some kind of random equation. Okay, all you've got to do is just put the numbers in. So 2 times by h, so h was 2.5. So 2 times by 2.5 metres divided by t squared, well that was 0.74, so divided by 0.74 squared, and that answer comes out as 9.13 metres per second squared. Part 2. They record the time t for 2 more drops from the same height. The 3 values for time t are that, and that. Calculate the average value of time t to an appropriate number of significant figures. So to get the average, just add that to that to that. Make sure you press equals, then divide it by 3, and that'll come out as 0.746. That's the 2 significant figures, so's that. So let's put our answer to 2 significant figures. So that'll round up to 0.75. Question C. Explain one way the students could improve their procedure to obtain a more accurate value for G. So remember, what they've done is they've held the ball at the top and they've just dropped it with their fingers and started the stopwatch, and then they've stopped the stopwatch when it hits the ground. So how do we know that they've started the stopwatch perfectly when they've dropped it? And how do we know that they've stopped it perfectly when it hits the bottom? Why don't we use a computer to measure the time? And that will eliminate human error due to reaction time. Part D. A car travelling at 15 metres per second, so that's the initial speed, comes to rest, that means it's stopped at 0, in a distance of 14 metres. So that's our distance that it's travelled, x. And the final velocity we call v. When the brakes are applied. Calculate the deceleration of the car. So deceleration is the same as acceleration, and it says use an equation selected from the list of equations at the end of this paper. Now I've seen these questions before. That's why I've called the distance x instead of d. Now if we go down to the end of the paper, there's the equations sheet, and we're looking for an equation that's got final velocity, initial velocity, acceleration and distance. So this is the equation we need to use. So if we go back up and we'll write it in, v squared minus u squared equals 2 times by a times by x. Now we need to rearrange that to get a. So that is v squared minus u squared over 2x. Bang the numbers in and out pops the answer as 8.0357. Now they've gave the answers and there's no decimal places. So I've just put my answer to 0 decimal places as well. We didn't have to. We could have just left it like that. (5a). Which of these is a non-renewable source of energy? If it's non-renewable, that means you can't renew it, which means one day it's going to run out. Geothermal will never run out because it's about the hot rocks inside the earth. Natural gas, yes, that'll run out. Okay, so that's your answer. Tidal, no, that won't run out. As long as there's a moon pulling on the oceans and the seas, there'll always be tides. And solar, that'll never run out as well. Well, not for 5 billion years, once the sun comes to the end of its life. Part B. Explain why renewable sources provide an increasing fraction of the electricity supply for many countries. Well, it's as simple as this. The non-renewable stuff is running out. Now, we want to create electricity. So if non-renewable sources are running out, we've got to use them less, which means we need to use more renewable. So as a percentage, as a fraction, renewable is increasing. You could also put down a reason why we're using non-renewables less. Non-renewable sources that cause pollution, as well as they're running out. Don't just say pollution. Give an example and be specific about the kind of pollution. So I've said coal causes CO2 gas to be released, which is what we call the greenhouse gas, which is causing global warming. Question C. Electricity can be generated using a water turbine. Water gains kinetic energy by falling from the top of a dam. Calculate the minimum height that 7 kilograms of water must fall to gain 1300 joules of kinetic energy. Now, if you're going to have 13 joules of kinetic energy at the bottom, that must mean that it had at least 1300 joules of gravitational potential energy at the top. And we're assuming that no energy has been lost on the way down. Now, the equation for gravitational potential energy is mgh, which is mass times by gravity times by height. We know that gravity on Earth is 10 newtons per kilogram. They won't give you that. They expect you to know that. Now, let's rearrange that equation. So we've got height equals GPE over the mass times by the gravity. Put the numbers in. Out comes the answer, 18.57 metres. That's how far the water has to fall in order to have that much energy at the bottom. Part 2. As water enters the turbine at the bottom of the dam, the kinetic energy of 8 kilograms of moving water is 1,100 joules. Okay, can you calculate the speed of the moving water as it enters the turbine? Now, we've got kinetic energy, we've got mass, we're trying to work out the speed, which is the velocity. So those three things are related by this equation. Kinetic energy equals a half mv squared. A half times by the mass times by the velocity squared. Now, if I know I'm rearranging the equation, I will write it as kinetic energy equals mv squared over 2 instead of the half. All right, it's the same thing. Now I can rearrange it just by simply bringing that 2 across to this side. So multiply both sides by the 2, and I'll get 2 times by kinetic energy equals mv squared. Now I'll take m over to this side. So I'll end up with 2ke over m, and that would give me v squared. I don't want v squared, I want v. So I'll square root both sides. And that'll give me v equals the square root of 2 times by the kinetic energy divided by the mass. Now that's a pretty standard equation, pretty standard rearrangement. It's quite a hard rearrangement, so have a look at it, make sure you learn it and understand it. Put the numbers in, out comes the answers. All right, 16.58. Part D. Moving air can be used to generate electricity using a wind turbine. Figure 6 is a graph of kinetic energy against wind speed for a mass of moving air. Alright, so there's the wind speed along the bottom, and that's how much energy the wind has when it's travelling at that speed. Just before the air reaches a wind turbine, it's got a wind speed of 15 metres a second. When the air has gone through the turbine, it has a wind speed of 13 metres per second. So it's lost 2 metres per second as it went through the turbines. As the air moves through the turbines, some of its kinetic energy is transferred to the turbine. Use the graph to determine the percentage of the kinetic energy transferred to the turbine from the air. Right, well, what we're going to have to do is we're going to have to work out how much energy is lost by the wind. So at first, if we can find out the energy at 15 metres a second, and we can take away the energy at 13 metres a second, we'll be able to work out how much energy has been lost by the wind and transferred to the turbine. So using the graph, at first the wind's travelling at 15 metres a second, and we can see that that corresponds to an energy of 5.2 kilojoules. Once the wind comes out the other side of the turbine, it's only travelling at 13 metres per second, which corresponds to an energy of 3.9 kilojoules. So the energy at the start was 5.2 kilojoules, and the energy after it's gone through the turbine is 3.9 kilojoules. So that means that it's lost 1.3 kilojoules. Now that's the energy that will be transferred to the turbine from the wind. Now what we need to do is work out the 1.3 as a percentage of 5.2. So to do that, the percentage transferred will be the energy change, or the amount of energy you've transferred, divided by the total energy that you had at the start, and multiply it by 100 to get it as a percentage. So the energy transferred was 1.3 kilojoules. It had 5.2 kilojoules of energy when it was travelling at 15 metres a second. So that comes out as 25%. So 25% of its energy has been given to the turbines. And that makes sense, because 1.3 multiplied by 4 would be 5.2, okay? So 1.3 is a quarter of 5.2. So 1.3 is 25% of 5.2. Question 6, Part A. The student investigates the relationship between force and acceleration for a trolley on a runway. Figure 7 shows some of the apparatus the student uses. Now I've drew this in. You'll find out why when I get down to Part 2. Part 1. Describe how the student could increase the accelerating force applied to the trolley. Right. Well, what's going to make the trolley accelerate over to the right? It's going to be determined by how much weight is on the hanger. Okay. So if I want to make it accelerate more, add more weight onto the hanger. Now you can see how I break my answers down using bullet points. It's worth 2 marks, so I do 2 bullet points. Part 2. Describe how the mass of the moving system can be kept constant. So first of all, what confuses students is, what is the moving system? Well, it's just anything in the system that's moving. So it's the trolley with the card, it's this wire, and it's the weight hanger. So I believe that there's a little bit of a mistake here. Normally what happens is there be some masses already on the trolley. And if we're going to keep the mass of the moving system constant, if we're going to add more weight to the hanger, we need to make sure that we're not just bringing weight in from anywhere. We need to take the weight or the mass off the trolley and pop it onto the hanger. Okay, it's a standard question. I've seen it lots of times over the last 20 years. So the answer is transfer the mass from the trolley onto the weight hanger. Part 3. Explain how the student could improve the procedure to compensate for the effects of frictional forces acting on the trolley. Now, frictional forces, if you're wanting to, decrease frictional forces, you'd say something like oil or lubricate the trolley wheels. You might even say lubricate the pulley, although I wouldn't in this case because they haven't even named the pulley. So I would stay away from that top answer. What we're going to try to do then is, if we take this runway and if we prop it up at this end like this, you need to detach the weight hanger first. So you'll see there's no weight hanger on this one. Now what we want is, we want that car to just start to move at a steady pace. Don't want it to accelerate down this slope. And what we've done there is we've compensated for any friction that would hold the trolley back, because the trolley's ready to roll down the hill, to roll down the runway. Okay, so raise the start of the runway so the trolley just starts to move at a constant speed, and obviously make sure you disconnect the weight hanger first. Part B. Figure 8 shows two objects, Q and R, before and after they collide. Okay, so before Q is moving, R is not. After the impact, Q is moving and R is also moving. The arrows show the direction of movement of the objects. The arrows are not to scale. Explain how momentum is conserved in the collision. Use Newton's third law and Newton's second law in your answer. Newton's second law can be written as force equals change in momentum over time. So normally it's force equals mass times by acceleration. But we can substitute out acceleration and the formula does indeed become this. Now, it's a big 6 marker. This is the last question on the paper. Look, nothing else to follow. So, what is momentum being conserved first of all? Well, I'm just putting down the basics first. I might get a mark for it before I'm even explaining things properly. Momentum is conserved is basically the momentum before is equal to the momentum after. Okay? I might get a mark for that. I might not. What is momentum? Well, to calculate momentum, it equals mass times by velocity. That's supposed to be an equal sign. My apologies. And also, what's Newton's third law? Well, Newton's third law states for every action there's an equal but opposite reaction. So we can expand on that. We can say when Q collides into R, there is an impact force. Okay, so that's what I've drew up here. How do we go from the before to the after? Well, at some point Q is going to impact with R. Now as Q impacts with R, Q will put a force onto R. Now Newton's third law says that R will therefore put an equal but opposite force onto Q. Okay, so the force of R on Q will equal the force of Q on R. However, they're in opposite directions, so you've got to put the negative sign in, okay, to show that you understand that. Now, if we use this equation, force is change in momentum over time. So the force of R on Q, we can now change that force for change in momentum of Q over time. Okay, so I've just took force out and I've put that in. Okay, I've took force out and I've put that in. Now, that will equal the change in momentum of R over time. But obviously, make sure the negative sign's still there. Now, the time for the collision, okay, is the same for Q and for R. So when, just say Q bumps into R, and it takes 1/10 of a second while the impact. Well, it also means that the impact of R on Q will also be 1/10 of a second, won't it? So that's what that means. Time for the collision is the same for Q and for R. So what that means, so that time there and that time there will be the same, so we can get rid of them. So that will just leave the change in momentum of Q is equal to the negative change of momentum of R. In other words, R is going to speed up and Q is going to slow down. In other words, the momentum is going to be transferred from Q to R, right? So Q is going to slow down, so that's going to lose momentum. Remember, momentum is mass times by velocity. So if Q is going to slow down, it's not going as fast as it was before because it gave some of its momentum to R. So Q is going to slow down. It loses momentum, and R is going to speed up. So it's going to gain momentum. And basically, the momentum that Q loses when it slows down is equal to the momentum that R gains because it speeds up. And therefore, we've proved that momentum is conserved during the the collision? Now that's quite a tricky question, but there's enough there, I hope you understand it, to get the 6 marks. If you don't understand it, pause it, work through it again. And that's that. So I hope that's been useful to you. Hit the like button, make sure you subscribe to my channel. There'll be lots more videos coming as you're getting into your mocks. Work hard, be nice, and bye for now.